So it's going to look like that. I'll have 1/2 of my mass, which is 0.2 kilograms, times the speed, which is v cosine theta, which is 35 meters per second, cosine of 30, and then that whole quantity, you have to square it, and that's equal to 92 joules. You'll see some problems like that that are just, you know, this thing is traveling at a certain speed. What is its kinetic energy? You also see some problems that are related to the work energy theorem. The work energy theorem just simply says that if I do work on an object, we've already seen this actually, if I do work on an object, I change its energy. That is the work energy theorem. And it says that the net work is equal to some change in energy. We'll typically say that this work changes our kinetic energy, and that's the way we'll deal with it primarily. But we've also seen where if we do work on an object, we change other types of energy. Like if I take this object and I apply a force over a certain distance, I've now changed its potential for motion, or its potential energy. But we'll also think about the work that we do and how it affects the kinetic energy, and that's primarily how we'll look at the work energy theorem. So in short, if you do positive work on an object, then you increase its energy. And if you do negative work, then you decrease its energy. Hopefully that sort of makes a little bit of sense, right? Because remember, negative work, if I have an object that is moving in this direction, that its displacement vector is to the, to the right, and my force is in this direction, I'll call it a little f, like the frictional force, then this force is doing negative work because it's opposite the displacement. And since it's doing negative work, that means it's taking away energy from that object. It's causing it to slow down. So let's say here, I apply a force of 3 newtons to a 2 kilogram block over a distance of 4 meters, and I want to know what is the block's final speed. So what I do here is I find the work done by this 3 Newton force, and then I say that work is equal to my change in kinetic energy, and then I can solve for what is the new speed. So first of all, ask yourself, what is the work done by this 3 Newton force? Oh, it's 12, right. It's 3 newtons times 4 meters, force times displacement. We're assuming here, since there are no angles, that it's all in the same direction. So I say F times D cosine theta, but we'll let theta equal to 0. So that's cosine of 0 is 1. So this is going to equal 3 newtons times 4 meters. That's equal to 12 joules. Now, how can I find its speed? I know that by doing this work, I've given it 12 joules of kinetic energy. And now I want to figure out what is the speed of this object. Now, we could have worked this problem with kinematics, right? We could have said, well, this force on this mass has a certain acceleration, and this acceleration is over 4 meters. So I can figure out its speed. I'd have to figure out the time that it takes to travel that 4 meters, and then I could figure out what is the speed at that time. But this way is a lot simpler and a lot easier to approach, because if I know its energy is 12 joules, the work that's done is 12 joules, then I know that has to equal to its kinetic energy at that point. I've put in 12 joules of energy into this object, and now it has a certain speed. So I solve for that speed. I say 12 joules equals a half of my mass, which is 2 kilograms, times v squared. This becomes a 1, half of 2 is 1, and so v is the square root of 12, which is, you know, about 3 point something. I don't have it, it's 3 point something meters per second. All right. You'll see some problems like that too. I have a force acting over a certain distance. Now what is the speed of this object? You'll also see some discussion of conservative versus non-conservative forces. Now, not in the terms of like, Trump versus Clinton, but in the terms of forces that conserve energy or not. So whenever I talk about conservative or non-conservative things in physics, we are, yes, sorry, I saw a question bubbling around. What's that? Oh, the second part, yeah, good. Thank you. So what if there's a frictional force of 1 Newton? Well, there are two ways that we could look at this. We could think of this object that has 3 newtons in one direction and 1 Newton in the other direction. And then the net force would be 2 newtons, right? 3 minus 1. And then we could figure out what is the work done. Well, it would be the force, which is 2 newtons, over 4 meters. And that would be 8 joules. And then you would go through this whole bit where you say 8 joules is equal to 1/2 mv squared. There's another way to look at this too, which is similar but different, is that you could think about what is the work done by the 1 Newton force. And the work done by the 1 Newton force is 1 Newton times 4 meters. And then you ask yourself, is this work positive or negative? And since it's going to be opposite the direction of motion, then this force will be in the negative direction, right? Because it's negative 1 Newton. So this work is negative 4 joules. And then the work done by the 3 Newton force is 2 newtons, or 3 newtons times 4 meters. And that's equal to 12 joules. And then to do the net work, it would equal negative 4 plus 12 joules, which is 8 joules, which is the same as what we got over here. You could do either way. You could find the net force that's acting, and then find what work is being done by that net force. Or you can say, what is the work done by the frictional force, which is negative work, and what is the work done by the other force, the 3 Newton force. This is going to be positive work because it's in the same direction as the displacement. Is that clear? Juliana, excuse me, Olivia? Everybody else clear? I always see 1 or 2 questions like this on the exam. The good part about having 3 chapters on an exam is I won't go real deep on any of the topics. So you probably won't see stuff a lot more complicated than this as far as this topic goes. That's good news. And that's why I said before that students tend to do better on the 3rd exam. But it doesn't mean that you don't need to practice, because you really do need to practice right now. In fact, every day you should be practicing, even if it's just 20 minutes a day. Okay, so conservative and non-conservative forces, this refers to what they do with energy. And you might already have some idea about what's a conservative and what's a non-conservative force. Like, for example, what would you say the gravitational force is? Would you say that that's conservative or non-conservative? Does it conserve energy, or does it, when we think about conserving energy, the opposite of it would be to lose energy? So does the gravitational force lose energy? No, you might not know that already, and that's okay. But the gravitational force does not lose energy. But what about frictional forces? Do they lose energy? Yes, they do lose energy, because whenever you have friction acting, you get a lot of heat that's produced, and that heat just goes out into the world, and it, causes things to heat up. It's no longer usable energy, so we say that it's lost. So conservative forces is a force that conserves energy. That is the amount of work done by the force changes the energy by the same amount. That is the energy of the system. And gravity is a great example of a conservative force. In fact, do you recall we divided our forces up back in chapter 4 into 2 broad classes of forces? You remember what they were? Gravity was one of those broad, it was in one of those broad category of forces. Sorry, what? Okay, yeah, field and contact forces. So field forces are like gravitational and electric field forces, we'll get into next semester. But gravitational forces are a field force. That means they don't require contact. Any force that requires contact is usually going to be non-conservative. Right? Any force that does not require contact, like gravity, will be a conservative force. So there are really only two true conservative forces that we're concerned with. There's the gravitational force and the electric force. Because they never lose any energy. How can they, right? They never come into contact with anything, or they don't have to. So let's say that I have a 2 kilogram block. That means that the force weight is equal to 20 newtons. So I have to apply a force, say, of 20 newtons in order to move it a certain distance at a constant speed. So let's say that I move it by a distance of 2 meters. That means that I've done a work on this object of 40 joules. I say 20 newtons times 2 meters. They're in the same direction, the force and the displacement. So I've done work of 40 joules. Because this is a conservative force, the gravitational force has changed I've also changed the energy by the same amount. So delta E is also equal to 40 joules. The change in energy of this object. Take an object, I apply 40 joules of work to it. Now this object has 40 joules of energy. I've lost no energy. I haven't lost any at all. Non-conservative forces, on the other hand, do not conserve energy. Or if you want to think of this, you can think of them as they do lose energy. And a good example of this, well, really any contact force, but friction is a great example of a non-conservative force. So gravity is a good example of a conservative force. Friction is a good example of a non-conservative force. And the work done by, friction, if I have friction, it does a certain amount of work, and that work is lost to the system. It's lost. That's why we have it as negative, because we take away that work. The work done by conservative forces is path independent. The work done by non-conservative forces is path dependent. Say I have this battery here. If I drop this battery, it falls to the ground, it gains a certain amount of energy because the gravitational force is acted upon it, pulling it towards the Earth. It's done a certain amount of work. All of that work now goes into the energy when it reaches the ground. And we can figure out then how fast it's going if we say, well, the work done by gravity is equal to the kinetic energy that it will have at the bottom. But the amount of energy that it has at the bottom is actually not dependent upon the path. It doesn't matter if it goes from this point down to that point. I can also have it take a different path. Let's see if this works. I can have it take a different path where I just have it, fall in a different way. So let's go over there. The gravitational force has now done the same amount of work on the object, and it has that same amount of energy that it gained from the gravitational force. Let's think about this slide. I have two people. They go down a slide. One person, they both start at this point, and one person just jumps and he goes straight down. And the other person follows a slide, so he takes a different path. Which of these people will have more energy when they reach the bottom of the slide? The person here or the person here? Which person? The first person or the second person? Which will have more energy when they reach the bottom? The person that just jumps straight off the slide or the person that slides down the slide? Which will have more energy? The first or second? The first one will have more energy. Right, you already jumped off like a cliff or whatever it is? You go pretty fast, right? There's no friction. Right, exactly right. There's no friction. The only force that's acting upon you is the gravitational force. And so this person has only the gravitational force. So no energy is lost. As a result, this person is going fast, and this person over here is going relatively slow in comparison. And the reason this person is going slower is because I have a frictional force that is acting all the way up, all the way down, the entire path of the slide as it goes down the slide. And this frictional force is continually taking away energy, taking away energy, taking away energy, all the way down the slide. You can imagine, too, that what if you had different slides? What if I had a slide that followed this path, the path that you have there, and then I had another slide that went like that, and then I had another slide that went like that. They all follow the same height. They all begin at the same point, and they all end at the same point, right, at the same height. But which one will be going slower? Let's see, we'll call green A, call red B, and call blue C. So which person will be going what did I say, slower or faster? We'll say slower. Which person here will be going slower? The person on slide A, which is in green, the person on slide B, which is in red, or the person on slide C. Which person will be going slower? And remember, non-conservative forces are path dependent. So it does depend upon the path that you take as to how much energy you lose. Which person will be going the slowest of all of these? All right, let's stop at 50. Awesome. Right. So A, it's a longer path. So it has more distance for the frictional force to act. And since it has more distance for the frictional force to act, this is big, so the work that's done by that force is also big. Because non-conservative forces are path dependent, it does depend upon the path that you take. Oh, let's see, I don't know if I told you this one. What do you do to a frog's car when it breaks down? It gets towed away. Okay? So they will not give the same energy. Okay, so regarding conservative and non-conservative forces, just know what they are. Know that conservative forces conserve energy, non-conservative forces do not conserve energy. Also know examples of both. Gravity is a good example of a conservative force. In fact, it and the electric force are really the only conservative forces. But we'll often make assumptions about other forces being conservative. And friction is a great example of non-conservative forces. Also understand this whole idea of path dependence versus path independence, and how that differs and what that means as to how you determine the amount of work done by force. Okay? All right. Let's look at gravitational potential energy. This is similar to what we've been doing. I think I've actually worked through this already, but we'll do it again now. So if I have this object that I move through a certain distance, let's say that I move it through a height h. Move it through a height h. There is a force weight, which is equal to m times g, and then I have to apply that same force, m times g, to make it move at a constant speed. If it accelerates, actually I have to apply a bigger force. But let's say I'm moving at a constant speed from this point up to another point. I've done a certain amount of work on this object. Remember, work is equal to my force times my displacement times the cosine of theta. The force that I've applied is m times g. The distance over which I've applied it is this distance h. And the angle between the two is 0 degrees. So this just goes away because the cosine of 0 is equal to 1. So theta equals 0, cosine of 0 degrees equals to 1. And so that work is equal to m times g times h. And now this object, which I've applied a force over a certain distance, it now has what we call potential energy. Potential energy is equal to, then, m times g, which is times h. That's just the work that we've done. So this comes through the work energy theorem. Our potential energy is m times g times h. Sometimes you'll see this written differently, and sometimes I might write it differently. You might see it written as PE for potential energy, as mgh, or in other books. I won't do this in this class, but if you're studying for this elsewhere, for the MCAT or whatever, you might see P written as U, where U is our potential energy. Okay, so if you see that elsewhere, that's okay. Don't be thrown off. That U is our potential. All right, let's see. Where did we leave off in this? I'm not sure if we're going to... We did all this, right? We do any of these? To work? We did this one? Yeah, we did this one, didn't we? The sign of energy? What number is that? 5.1 what? Oh. Oh yeah, we did all this, I remember now. We did this one? I don't... Oh, yes. I'm sorry, you're missing a page, unfortunately, or you have a page duplicated. One of you pointed this out to me earlier. I'm sorry, I think that there are just 5 or 6 questions that are not printed. I will place them online after we do them in class, so you'll have them after we complete them in class. So let's just start with this one, okay? But this one's not in your book, unfortunately. I'm sorry. Okay, so car number 1 has twice the mass of car number 2, but they both have the same kinetic energy. So K is the same for both of these, but one has twice the mass. How do their speeds compare? Might help you to write out the equation. I wouldn't try to do it in your head, but write out the equation. If you change the mass by a factor of 2, what is that going to happen to the speed? I'm going to mute it for just a second. All right, I'm going to stop at 2:05. Okay, good. B is right. First of all, I just want to think about if car number 1 has twice the mass but the same energy, is it going to be moving faster or is it going to be moving slower than car number 2? Car number 1 will be moving faster or slower than car number 2? It's going to be moving slower because it has twice the mass, but it has the same amount of energy. So more mass, same energy, so it's going to be moving slower. So that means that I can get rid of, well, I can get rid of this one, but I have to keep all the others. So I can get rid of D. So now the question is, by what factor is it going to be moving slower? Well, I know that 1/2 mv squared is my equation for kinetic energy, and they both have the same kinetic energy. So if I have 2 here, then that means I'm going to have a 1 over 2, or 1 over root 2, rather, here for V. Now, if you work the ratio then will work out that the V2 has to be root 2 times V1. So car 2 has 1.4 times the velocity of car 1. And car 2 is moving faster than car 1 by a factor of root 2. And it comes about because of this V squared here. My V is squared. All right. 2 stones, one twice the mass of the other, are dropped from a cliff. Just before hitting the ground, what is the kinetic energy of the heavy stone compared to the light one? I'm going to stop at 1 minute. Okay, awesome. D is right. I have 2 objects, one big, one small. They both drop. At the bottom, they both have the same speed because they're both accelerating at the same rate. And the energy then is going to be 1/2 mv squared. They both have the same velocity, but the heavier stone has twice the mass, so it'll have twice as much energy. It has the same speed, but twice the mass. In the previous question, what is the final speed of the heavy stone compared to the light one? All right, I'm going to stop at 25. Okay, awesome. See, are they have the same speed? All right. Let's see. What do you call a bear with no teeth? A gummy bear, right? All right. Let's try this one. I'll stop at 35. Okay, that's awesome. So I'm going from 2 meters per second to 3 meters per second. That means I have an increase of kinetic energy, which means that I've done positive work on this object. So A is the right answer. So I never wanted to believe that my dad, he worked on a road crew, that he was stealing from the state. But when I got home, all the signs were there. He didn't really work on a road crew. He worked at a tire shop. But positive work was done. Okay, let's try this one. This one's interesting. The car starts from rest and accelerates from 30 to 30 miles an hour. And then it gets on a highway and accelerates to 60 miles an hour. Which takes more energy? Going from 0 to 30 or 30 to 60? Or is it both the same? All right, we'll stop at 50. And y'all are sort of split up on answers. All right, so E is the right answer. Think about our kinetic energy. Kinetic energy is equal to 1/2 mv squared. Notice if I were to plot kinetic energy versus V, it would look like this. Kinetic energy, V, it's going to be a parabola. It'll look like that. And so as I go from 0 to 30, I take this much energy. But as I go from 30 to 60, I take this much energy. It takes a lot more energy to travel at higher speeds up here than it does at lower speeds. That's why your car is not a perfect argument with your car, because your car is sort of optimized to operate at a certain speed. And so, you know, if you travel, I don't know what the speed is, 45, 50, 55 miles an hour. But if you do travel at very high speeds, 70, 80 miles an hour, your gas mileage will degrade quickly, because it just takes a lot more energy to travel at large speeds. It takes a lot more energy to get that big old hunk of metal up to these high speeds, and then to keep it at those high speeds. So it does take more energy to go from 30 to 60 miles an hour. Is it possible for the kinetic energy of an object to be negative? I haven't said this outright, but I think that you can reason it out. All right, I'll stop at 30. Okay, maybe not so easy to reason out, but the answer is no, that the kinetic energy is never going to be negative. If you think about the equation, it's 1/2 mv squared. Even if our velocity is negative, although here we're actually dealing with speed, but even if our velocity were negative, you square it, it takes it away. Our mass is never negative, right? So the kinetic energy is never negative. It's a scalar quantity. Remember, our work is a scalar quantity too, but we can have negative works. Remember, that's sort of a special case. We don't usually have scalar quantities that take on negative values. But our negative work is a definition that we ascribe to it to describe what it does to the energy. Is it taking energy or giving away energy? But there's not a similar thing with kinetic energy. It's always going to be positive. Similar for, no, never mind. For kinetic energy, it's always positive. Is this one in your book? Yeah. We're going to skip it, though. I'm sorry. Were the previous ones in there? So we're sort of back on track. We are going to skip this one, though. The answer is E, but you can just sort of cross it out. And we'll do this one. there's two paths. One goes straight up the mountain. One sort of has a bunch of switchbacks. It's twice as long but less steep. How much more potential energy would you gain if you take the longer path? All right, we will stop at 105, 105. Okay, good, not great, that's okay. We gain the same potential energy. Because potential energy is a conservative force, it's path independent. It doesn't matter which path you take when you're thinking about the work done by the gravitational force. If I take this path or this path, all that matters are the 2 points that you begin and end at, the beginning and ending point. Now, it is true that one of these will take more work. Which of them will take more work? The switchback path, right? It will take more work. The red one takes more work. I'm sorry, y'all said steep, didn't you? Why does the red path, the one with the switchbacks, why does it take more work? More distance, right? And you have all sorts of non-conservative forces acting upon you. Now, it's harder to go up the blue line, right, because it's just steep, and it's just hard to climb steep things. But it takes you a lot less work to go this path than it does to take this path. But the answer to this one is the same. The gravitational force does the same amount of work, but the net work, if we think about the total system, then this one would require more work because you have this big frictional forces acting over a large distance. We'll come back to this next time. Let's look at conservation of energy. Conservation of energy simply says that the initial energy equals the final energy. What's implied in this is that we're dealing with conservative forces. Now, it would apply to non-conservative forces too if you could take into consideration all the energy that's lost. So when you have friction, if you can include things like thermal energy and the deformation of the surfaces and stuff like that, when you're taking into consideration non-conservative forces. But in this case, we're just going to think about conservative forces. So we're only really thinking about gravitational forces. So the initial energy is the sum of the potential energy and the kinetic energy. So P initial, actually I am going to call this PE here, kinetic energy initial, and then that's equal to PE final plus the kinetic energy final. Now whatever energy I have initially is going to equal the energy that I have final. And in every case, every problem that you see, when you'll see some in the exam, and we'll do some in here, you'll have potential or and kinetic energy. You'll have either or both of those. And then in the final state, you'll have either or both of these, the potential and the kinetic energy. So let's do an example. We'll wrap up soon. But let's say, listen, you're going to have an exam problem almost identical to this. Same scenario anyway. Different numbers, of course, but a very similar thing. I have this object. It has a mass of 100 kilograms. Acceleration due to gravity is 10. And its initial speed, right here, is equal to 10 meters per second. And I want to know what is, and then I also know that over here, that it comes to rest. So over here, V is equal to 0. I want to know what is H, what is the speed at this point, and then what is V at point C. Where's point C? That's the one I just drew. Oh, point C, it just got off the figure, is right here. I want to know what is the speed at point C, at that point. Okay? So first of all, I want to find out what is H. So I'm going to set up my conservation of energy, energy initial equals energy final, potential energy plus kinetic energy initial equals potential energy plus kinetic energy final. And then I ask myself the question, because often some of these will go away. In the beginning, does it have potential energy? Does it have kinetic energy? Remember, potential energy is mgh. Kinetic energy is 1/2 mv squared. Does it have potential energy? No, because I say that my initial height is 0. And I'm going to set my initial height at this point. And so I'm defining that it has no potential energy at this point. It's like setting our coordinate system. Now, it'll often be easier. In fact, I think it'll always be easier in this class to let our y equals 0 be at the ground level. So you'll see that as it comes up in problems. So it doesn't have any potential energy. So I'm just going to get rid of that. At point H, or up at this point, does it have potential energy? It does. It's going to be mg. I'll just call that H. Does it have kinetic energy? What do y'all think? It does not have kinetic energy. So that's 1/2 mv squared. But this is equal to 0, so this whole thing goes away. So what I'm doing here is solving for H. I know the mass, I think it was 100 kilograms. V was 10 meters per second, equals to 110 meters per second squared times H. Notice here, and we'll see this in some problems next time, that the masses cancel. So even if you don't know your mass, you can still find the height to which it goes. And I solve for H. The 10s cancel too, but for a different reason. Because, oh, this should be squared. Is that what you were saying? Yes. So I have 50 divided by 10 equals 5. And so that is my H, 5 meters. So that's part A. In part B, I work it exactly the same. I'm going to say my potential energy equals plus my kinetic energy equals the potential and kinetic in the end. But at h over 2, one of these is not going to go to 0. Which one is it? Is it this one or is it this one? Okay, well, here, this is my initial. So I need to think about what are my initial and final states. You can choose different initial and final states, but I'm going to stick with this one as my initial. But at my final state, this is going to be my final state. So the initial is still going to be the same. I'll still have no potential energy, and I will have kinetic energy. But what about the kinetic energy right here? Is this object going to be moving when it comes up over the thing? Yes, because I know actually it'll go up higher than that. You ever been on a roller coaster? Roller coaster? Yeah. Roller coaster. It comes up to its highest hill, and then it'll stop. But when it does those little short hills, that's where it goes so fast. We did a roller coaster over the summer. I think I might have shown you a picture from Six Flags. I'll tell you about this. Listen, my wife loves roller coasters. And we were kind of concerned that our kids are 8 and 11, and they're kind of, I don't know, they're kind of scaredy kids sometimes. So they're not always real brave. That's okay, they're kids. But we were afraid that they wouldn't be willing to get on the roller coaster. So as soon as we got into Six Flags, we said, let's go to the roller coaster. And they were all excited about being at Six Flags. And they're like, yeah, let's go to the roller coaster. So we got there. We were the first ones in line. In fact, nobody else rode the roller coaster with us. So we were right up front, right? My wife and daughter were in the very first car, and I was in the second with my son. And then we got going, and they were all really excited. And then the first hill. I'm like, oh, my son, he just sort of closed his eyes and said, no, no, no. He went off. But it was fun. They wouldn't get back on another one. We did get them on another sort of tame one, but we called it a train. We said that it was a train and not a roller coaster. All right, so let's do part B here. We say the initial is only kinetic, so that's 1/2 mv squared is equal to, in this final state is 1/2 mvf squared plus mgh. And this is actually going to be mgh over 2, because that is what our height is. Yeah, William?
What happens with first one?
Because it doesn't have any potential energy right here. And so I've canceled out this part. I could have written mgh. I could have written mgh initial, which would be right here. H initial equals 0, but this would go away and become 0. All right. I know everything here. Actually, I can cancel out my m's here, here, and here, and then I solve for h. I'm not going to do it here because we're out of time. But next time we'll do the third part, and it'll work out very similarly. It does work out to be, h works out to be 5 meters. No, it doesn't. No, I'm sorry. We don't solve for h, we solve for v. V works out to be 7 meters per second. All right, y'all have a great day, okay? We'll finish up this chapter next time and start the next.